Hey, Advanced Chem students, this will be our, I guess it's our fourth lesson on water. But you guys should have a half sheet of paper. This is kind of normal for us, this unit, right? Take out your half sheet of paper and make this chart. Make sure you write your name on it, but make this chart and rank from 1 to 3, from smallest to largest, what each of those are, the suspension, solution, and colloids. And then I want you to write an example off on the right-hand side, just one example of each one. Do this real quick and then turn it into the box. And you can just press pause right now while you get this done. And as soon as you're finished, you can restart. Okay, so if all those are in the box, and let's go ahead and move forward. So first thing I'm going to do is go over the homework problems with you. Sorry I'm not here to take a grade on it, but that's okay. I'm going to just go through and explain some of these. I will go a little quickly, so if you want to pause it and take a look at some of the written out work, if there's any math associated with it, just go ahead and do that. But chapter 15, homework 3, we'll go through these real quickly. So it says, write the formulas for these hydrates. You know, sodium sulfate decahydrate. If you see deca, that's going to mean that it's got 10 of the water molecules bonded to it. Sodium sulfate, yes, you guys, you know, I'm sure you know your ions, hopefully. Sodium and sulfate, and decahydrate means 10 water molecules. You'll need to write that out as, you know, appropriately. So sodium sulfate dot, since it's hydrated, the 10 H2Os. That's how you'll write that. If it's a dihydrate, it'll have 2. If it's an octahydrate, it'll have 8. And so what it should look like if you did these correctly should look like these over here on the right. So there's your sodium sulfate decahydrate, calcium chloride dihydrate, and the barium hydroxide octahydrate. Looking at the next two, let's see if I get to the next two. That's going to mess up with me a little bit. Epsom salt is magnesium sulfate heptahydrate. It changes to a monohydrate. It says write an equation for this change. So what you're going to want to do is go ahead and write the formula. I hope you did that. And you're going to change that to a monohydrate. So it'll just be magnesium sulfate with mere 1 water bonded to it. And then what would be left over? 7 water molecules. So that's sort of a dissociation, but it didn't let off all the waters. It just let off enough to leave it as a monohydrate. You know, you guys do need to know how to be able to write that. Some hydrates are efflorescent. What that means? Okay, well, to effloresce means to like give off water. So a hydrate loses that water. So efflorescence is the loss of water, is what they want you to say. It says here, all right, let's see. It says, why is it important to keep some hygroscopic substances in tightly sealed containers? Well, okay, if they absorb water from their surroundings like our NaOH did in the lab, what will happen is if you keep it closed, there's a small amount of water vapor in that jar, in our case, or in that container, that's going to allow that to happen. And so if you close it, you limit the amount of water that it's exposed to. And then that 54 is actually what I asked you guys to do at the beginning. Arrange colloid suspension and solutions in order of increasing particle size. Suspensions have the smallest, and solutions have the smallest, and suspensions are, of course, the largest. Colloids are kind of in the middle. Hopefully you would have done that correct at the beginning, but, you know, we'll see. Okay, so next it says, how could you distinguish between a solution, a colloid, and a suspension? You could use the Tyndall effect to do that. So what you could do is shine a light on it. The solution, it will completely, you know, go through. But as far as the suspension and the colloid, they'll actually scatter the light. And so you would be able to see that. Also, if you let the sample sit for a certain amount of time or for a long time, the suspension will eventually settle out. And so that could distinguish between a colloid and a suspension. Why don't solutions demonstrate the Tyndall effect? The particles are too small, so they're not going to refract the light, and so you're not going to see any deflections. So the molecules are just too small. 60, how can a colloid be destroyed? Well, the way that you do that is by what they are is their ionic repulsions between them. So if you add an ion to it, of an opposite charge, of course, or add an ionic compound to it that has both present, it'll actually destroy the colloid. And what will happen is the colloidal dispersion, the particles will kind of bond together with the one of opposite charge, and it'll pull them out of solution as precipitates. In 61, it says, what makes a colloidal dispersion stable? Emulsifiers, you could have also said surfactants. That would be okay too. Those things tend to stabilize colloids and create miscible or immiscible liquids to mix together and produce that colloidal dispersion. And then 75, last question, says barium hydroxide forms an octahydrate. Write the formation of that. What I would do, if you're told that, is to go ahead and write your product here, since it's barium hydroxide, and it's an octahydrate. You would write it with the 8 H2Os. Forming that, you would have a plus sign between the two. So you would have barium hydroxide plus the 8 waters forming the octahydrate. And then, of course, if it asked you to calculate the percent by mass of water, you would need to go ahead and calculate the mass of course, barium hydroxide with the 8 waters. That's there in the denominator down here. And then I would do the 8 waters separately and then divide the two together, and you'll multiply by 100 and you get that percent. And we did one of these in class yesterday, but I know it kind of slips your mind. You will definitely have to do this. We have very little math on this next test, so definitely be able to do this. Okay, so that covers the homework, and now we're going to move on to the notes. If you need to pause for a minute and get your notes out and stuff, we can do that. But I'm going to go ahead and get started. So, and if you guys want to go back and read this on the sinking feeling, it's fine. It's talking about salt domes and salt hydrolysis, or at least salt solubility and stuff. But anyway, moving on. So factors that affect the rate of solution. So there's things that you can do to make things dissolve, I should say dissolve faster, but if they're not going to dissolve, it won't effectively change it. And what they are is a quick and easy way to remember this. Let me get my pen going here. Is particle size, temperature, and agitation. One way to remember this is heat it, crush it, stir it. Or heat it, stir it, crush it. Or heat it, crush it, stir it. Heat it, crush it, stir it is how I say it. But what that means is if you heat it up, you can get it to dissolve more quickly. If you crush it into smaller particles, you increase the surface area and you can get it to go more quickly. Or if you stir it, if you make that solute come into contact with fresh solvent, it will actually allow it to dissolve faster as well. So those three definitions are perfect. And if you can remember it as heat it, crush it, stir it, you can remember those three things for making things go faster. Now, they won't make things dissolve that won't dissolve. In order to do that, you got to add like emulsifying agent or whatever, or surfactant. But this is just asking if it's going to happen. If you already know it's going to happen and you want it to go faster, you can increase that rate of the solution. It's not necessarily going to increase the rate of reaction, however, and that'll be a unit that we discuss next. Now, in terms of solubility, that's how much of that solute is going to dissolve in a given amount of solvent. Usually the solvent that we talk about is water. And that's what this one is talking about here. It's giving you, over on the left-hand side, grams of solute per amount of water over there on the left. And then down here at the bottom, it's a manipulation of that based on temperature. If you look at all of these graphs, almost all of them are increasing as you increase temperature. So as you go this direction, right, almost all of them are increasing. And so that means that, heating things makes them dissolve faster. Now, there are a few exceptions. Those that have really large numbers of ions, like cerium sulfate there on the bottom, you actually decrease the solubility, but we don't need to discuss that. For you guys, just understand that if you increase temperature, you are going to be increasing the solubility. And so you can get more of that solute to dissolve. Now, this is certainly true of sugar. I can't really. In tea, if you want to get more sugar to dissolve in the tea, you heat it up. Now, if you stir it, you won't get more of the sugar to dissolve, but you will get it to dissolve faster. But what it will reach is called the saturation point, or it will become saturated. And so that's what this slide is talking about here, is these types of aqueous solutions. Ones that are saturated have the maximum amount of that solute in a given amount of solvent at that temperature. If I go back, my bad. But if you look at the previous slide, sorry about that. If you look at the previous slide, it will show you the maximum amount. That was showing you how much would dissolve at a given temperature. In an unsaturated solution, more solute could be dissolved, so you wouldn't be quite at that saturation point. So if you put a little bit of sugar in the tea, you could still add more before it becomes saturated. Now, you can usually tell the difference between a saturated and unsaturated solution is because unsaturated has no undissolved solute. They don't have any solid present. Whereas a saturated solution, it could be exactly saturated, but if you add a little bit more and you see it at the bottom, it means that it was saturated. The last type is called a supersaturated solution. And I'm going to do, on the bottom, it's got little pictures here showing you what's going on. I'm going to demo this for you in a separate video so that you can see it, because it's quite awesome. I wish I were here in class to do it, and maybe you guys convince me to do it Tuesday when we get back. But I'll do a video of it that they can show you here in class, and you can see what happens with a supersaturated solution. With a supersaturated solution, more solute is dissolved per given mass of solvent than is possible at that temperature. And there's a way that you do that. The way that you do that is you dissolve all of it, which if you look at this picture here, let's see if I can get my pen going. They're dissolving that solute until they still have some present. And at this point, it is saturated. That 9 grams at the bottom won't dissolve. But if you change the temperature to 50 degrees C, it suddenly dissolves. Well, not suddenly, but whatever, it dissolves. Once it dissolves, you let it cool back down to 25 degrees C, and it's possible that the solute molecules will stay suspended in solution. Kind of like a colloidal dispersion, but not really. They're just staying suspended in that solution. If you do something to it, like you agitate it or you add a little bitty seed crystal of something that disrupts that suspension, they'll actually come out and recrystallize the entire solution. Now, this picture says that they're just going to turn into the 9 grams you had before. That's not what happens at all, and I'll show you, excuse me, an example of what that looks like. It's quite awesome. But to form a supersaturated solution, you've got to put more solute than will dissolve, heat it up so it all dissolves, cool it back down, and then add a little seed crystal and see what happens. You guys will do this in our solutions lab next week. So miscible versus immiscible. This really sounds like mixable versus not mixable, I guess. It means the same thing. Miscible means a liquid in a liquid. It's not about mixing a solid in there. It's about two liquids, mixing together. Things that are miscible are going to be polar. It's going to be like dissolves like. So polar substances and other polar substances like ethanol and water. And immiscible things will be like oil and water. Our example of the little blue liquid and the colorless liquid. They don't mix together because of their polarity. If something is added to them, it's not that you make them miscible, but you can combine them, but you need a compound in order to do that, an emulsifying agent. So solid solubility is almost entirely, like I said before, this is the same graph from before with a little bit of color. At a higher temperature, more of those molecules are able to come into contact, and so it becomes more soluble. There are a few that become less soluble. They usually have a large number of ions, but almost everything, as you increase temperature, they become more soluble. Now, that's for solids. That's not true for gases, but it is true for solids. So here's an example of a calculation with this in terms of solids. It says, what mass of sodium nitrate can be dissolved in 250 grams of water at 20 degrees C? So what I'm going to do is come over at, I'm going to read the solubility from the graph, but if I go over 90, it's really not 20 degrees. We're kind of lying here with this graph. It's really, I don't know, at 20 degrees C, it's not quite 90. So 90 is really kind of down here at about 22. But let's lie, since the way the PowerPoint is done. We'll go ahead and say it's at 20. So we'll say 90 and 20. Guys, this is just a simple proportion. You'll take 90 over 100 if you want to solve for the amount that's at, let me get my pen, at 250. You do 90 grams per 100 grams of water equals X grams per 250 grams of water, and you can solve. It's merely a proportion. Just a ratio to find out that number of grams. Now, I agree, this is really kind of sad. Maybe it's a number of sig figs here or something, but it probably should have been more like, 22 degrees or, I don't know, maybe 88 grams instead of 90. But this is okay to understand what's going on. So, but yes, if you do increase that temperature, if we were to increase that temperature further over this way, say to 50 degrees, and I go up, I can get, almost 114, 115 grams to dissolve. So it makes a difference based on how hot it is or what the temperature is or how many of those molecules are going to be able to contact other molecules at a higher temperature. With gas solubility, it is the opposite. And you probably know this. If you heat up your soda, you're going to drive that CO2 out of the soda. And that's absolutely true here. And I'm going to do a little demonstration with the supersaturation demo showing you this in terms of like soda. I'll take some soda and I'll put it in cold, and I'll take some soda and put it in hot, and we'll look at the bubbles and see what happens as a result. Gases, though, are always soluble at lower temperatures. So what you should see in the demo, and you will, is that the bubbles in the solution tend to stay in the solution that is cold, and they don't tend to stay in the solution that is at a higher temperature or warmer. So Henry's law is that it is in terms of pressure. So you're looking at the solubility of things based on pressure, and it's gases. So it's just S1 over P1 equals S2 over P2. There is a direct proportionality to increasing pressure. You can increase the number of gas molecules that are present in there. And so that would increase that pressure of that gas. You can increase the solubility or number of moles of that gas in that solution. And we've got a little example here. So, it says at 25 degrees C, the solubility of a certain gas in water is 0.75 grams per liter at H2O, of H2O at a pressure of 1 atmosphere. So that would be your S1 and your P1. It says, what is the solubility of the same gas at 10 atmospheres of pressure? So you can get more of it to dissolve. It is, of course, just a simple proportion. It doesn't even really matter if you do solubility on top, S1 over P1. You can reverse it or reciprocal. It's fine. But try this one. Hit pause. Go ahead and try. Very simple. Get your answer and then play again and take a look. So yeah, hopefully you remembered to go ahead and list all of your variables, but your solubility one was the 0.75, and then of course 1 atmosphere for your initial pressure, and then your final solubility would end up being 7.5 from this proportion at a final pressure of 10 atmospheres. So you can get quite a bit more to dissolve by increasing the pressure. So what I'm going to do is I'm going to make a separate video for you guys demonstrating those two demos I talked about. Otherwise, after the demonstrations, you guys are going to have time in class to work on your homework. Please do that. Use the time wisely. If you need to take pictures of the textbooks in the back to have the answers, listen to me, the questions, that's fine. But be respectful and use your time wisely, okay? See you guys next week.